Hello, 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 hello. multifaceted contributions of one of the greatest physicists of the 20th century, both his scientific achievements and his enduring legacy. Let's give a warm round of applause for Professor Rajaram Nityananda sir as he takes the stage.
I hope this informal arrangement of the mic is working. Actually, because of fear of Bangalore traffic, came here almost 1.5 hours early. I'm very happy I did, because I got a chance to spend time in the physics department, learn a lot about the department, the whole program, and really nice to see so many people from an engineering school coming in to a talk on astrophysics, and in fact having a thriving astrophysics club. Okay, let me see if I can keep it at the right distance. So what I wanted to do today, it's not so much an astrophysics talk, because it's more about an astrophysicist, but there will be astrophysics in the talk. And he's truly an extraordinary person, not just as far as people born in India are concerned, but even on the world scene. Okay. This program was originally announced for October 19th, and therefore I couldn't resist planning this talk, because that happens to be his birthday, 1910. Okay. So here is a picture of him at somewhat advanced age, very dignified, serious. And what's remarkable as compared to other people is that he would work intensively in an area for about a decade, write a series of papers. They would be very relevant to astrophysics, but also have a certain mathematical beauty of their own, because he loved mathematics. And then many people get trapped in an area, but he deliberately would move into a completely different area. And so I'm going to start by mentioning 6 books and the dates of their publication. And that gives you an idea of the various stages he went through in his life. And by the way, the stellar structure book sort of terminates his period in which he was working on the structure of a particular kind of star called a white dwarf, which we'll talk about in detail. That's what won him the Nobel Prize. Now, many Nobel Prize winners have this problem. Once you won the Nobel Prize, what do you do after that? Right? But he did not have that problem. And that's because he changed his field. Okay. So I will spend the maximum time on his Nobel Prize winning work and explain to you some of the physics behind it. And the remaining topics, I'll have to be a little more superficial, but I hope I'll give you a feel for those as well. And if, of course, any of you want to know more, my email address is up and I can put you in touch with the appropriate sources. So these are just the titles of the books. I'll be telling you what they are about. And you can see the length of the career, right? He was born in 1910. So he's 73 years old when he publishes this extremely scholarly and difficult book on the mathematical theory of black holes, okay? And which involves Einstein's theory of gravitation. It's a subject so difficult that usually it's a young man's game. And he started learning this only at the age of 60. So that tells you again that he was very unique in many ways amongst theoretical scientists. So this is to tell you that all the books are available on Amazon, and they should certainly be in your library, right? You can look at them. Of course, in most cases, the subject has moved on, but many of the things he wrote are still quite relevant, okay? Now, when so I've told you he had 6 phases of his career. So when I was preparing the lecture, I told my colleague, I gave him the title. It didn't say phases, it said faces, okay? So you can see the answer to the faces is in Rajarajeshwari Nagar, not far from here. His name is Subramaniam, and another name for the same idol is Shanmukha, which is six-faced. So I could not resist making this mythological connection. Now here is Chandrasekhar at the age when he must have made his great discovery. So 1930s in Cambridge. And if I didn't tell you that this was a famous astrophysicist, and I told you he was a famous film star, I think you would agree he's extremely handsome, right? And this is 50 years later. And you would think that he's a film star because, look at all this publicity, the cameras and so on. This is October 19th again, but October 19th, 1983, by coincidence, that's the day on which he was awarded the Nobel Prize. Okay. So he normally has a very serious face. You can see a slight smile on his face. There's an anecdote from this later period. Young woman from Italy called Valeria Ferrari signed up to work with him. Right? He worked with many very young people late into his life, and they were all very happy with working with him. And when she landed there, this Nobel Prize announcement was made, and she was terribly disappointed. She said, "Look, anyone who gets the Nobel Prize is simply too busy, and I'm not going to be able to have any time with him." And she records that 2 weeks later, they wrote their first paper. So this shows how devoted he was to his subject and his students. Okay. So the topic on which he first worked, technically the work was done in Cambridge, but before that, up to the age of 20, he was educated in India, in Presidency College, in Chennai. But he also had the opportunity to meet some famous physicists in Kolkata, where his uncle had already won a Nobel Prize. That is C.V. Raman. Okay. And in particular, he learnt about the quantum mechanics of electrons, which is now a subject which I think all of you are taught, Fermi level and all that, right? And he's at the age of 20 and he takes the ship to go to England. So I think neither country can claim the credit. Somewhere on the ship, he had this idea that the theories underlying a particular kind of star have a gap. And this has to do not with stars like the sun. A star like the sun is held up against gravity. After all, it's a very massive object. So you can ask the different parts, why don't they just fall to the center? And the answer is that there's a huge pressure in the center. And the pressure is because of the temperature. Okay. And then why is there a high temperature in the center? Because of nuclear reactions. But nuclear reactions are a source of energy, but they're not infinite. Okay. The sun is about halfway through consuming its nuclear fuel, which is hydrogen. Actually, the nuclei of hydrogen, protons, which by a chain of reactions get converted to nuclei of helium, alpha particles. And this process releases energy. It releases energy 1,000,000 times more than any chemical reaction would release. Okay. So this fusion process, the last hydrogen can be converted to helium. And helium is a nucleus with a higher charge than hydrogen. So to make two helium nuclei fuse together requires a still higher temperature, and so on. So depending on the mass of the star, this fusion process continues. And in the case of a star like the sun, which is not very massive, okay, it stops. Once carbon and oxygen are formed, it's not able to burn. That's the terminology which astrophysicists use. It's not able to burn these because now carbon has a charge of 6, oxygen has a charge of 8. Pushing two such nuclei against their Coulomb repulsion is very difficult. So the star starts to shrink. Okay. And this was understood around a little before Chandrasekhar made his journey. And a particular kind of star had been discovered late in the 19th century, which did not seem to be having nuclear reactions in its center. It was very small, so it was called a dwarf. Okay. And the surface was very hot, right? But it did not have a hot interior. And the puzzle of holding up such a star against the force of gravity was solved even before Chandrasekhar by a physicist called Fowler in Cambridge. In fact, Chandrasekhar went to work with Fowler. And Fowler's basic idea was that The quantum mechanics had just been discovered, and the same problem can be asked of a metal. It has electrons, it has positive charges. Why don't they just attract each other and collapse? And the reason is that as you bring them closer and closer to each other, the energy of the electrons goes up. You could say due to the uncertainty principle, right? If you confine something to a smaller volume, its momentum goes up. And the other principle is the Pauli principle. So once you have some electrons occupying some states, other electrons have to come to states of higher energy. So even at zero temperature, a gas of electrons will exert pressure. So that's the basic physics. Okay. So incidentally, Sirius is a very bright star, which all members of any astronomy club know. But there's a very faint star orbiting it, and it was the first member of this family which was discovered. It's called Sirius B. I doubt that one can see it with an amateur telescope, but you could try, right? And people could measure its mass by the gravitational force which it exerts on Sirius. The mass was comparable to that of the sun, but its radius was only 1%. Okay. How do you know the radius? You know the total energy which is coming from the star. You know its temperature. And then the laws of radiation tell you with so much area and so much of a temperature, you know, what would be the amount of energy coming out. Okay. Just the basic physics, which is taught in the first year, enabled people to conclude that this so-called white dwarf star was just 1% of the size of the sun. So sun is about 1 million kilometers in size, and this will be more like 10,000 kilometers. This is more like the size of the Earth. So I've already told you this. The interesting thing about white dwarf stars is that the more mass you add to it, the radius shrinks. Now, I'll try and be a little more quantitative. What is the force of gravity or the pressure which has to be opposed by the electrons? Now, you can just imagine a thought experiment in which the star is cut into two halves, m by 2, m by 2, and then they attract each other with a force which is proportional to m squared. And the area over which this force is distributed is proportional to r squared, okay? So the pressure already has a factor of r to the minus 2, okay? Right? R squared, no, I'm sorry, it's m by r squared, that's the law of gravity, and one more r squared for the area. So it's r to the minus 4, okay? So if you can produce a pressure inside which increases faster than r to the minus 4, you can stabilize the star. And that is what Fowler did, okay? He studied the pressure due to electrons, okay? And that comes out to be r to the minus 5. And again, it's not that difficult to understand because one thing is the pressure of any gas will depend on its density, the number of molecules per unit volume, right? So that's already one factor of r to the minus 3. The remaining r to the minus 2 comes from quantum mechanics, the uncertainty principle. If you confine an electron to a smaller volume, its energy goes up. And therefore, its pressure, its speed goes up, okay? So that's how the r to the minus 5 came. So if you have one curve rising as r to the minus 5, another curve rising as r to the minus 4, the two will intersect. And for smaller r, the electron pressure will win. Okay, I'll show you a graph later. But inspiration which Chandrasekhar had on the ship was that this increase cannot go on forever. Now, for that, we have to understand a little better the pressure of a gas. On the one hand, it will depend on the number of molecules striking the wall, right? Which depends on the density, as I told you, also depends on the velocity, okay? So that alone will give one factor of V. And V is proportional to 1 by R by the uncertainty principle, okay? Then there's one more factor of V because of the momentum which these carry. And the pressure is just force per unit area, which is momentum transferred. So there are two V's. That's how we got the remaining two factors of R. Now, what Chandrasekhar realized is that if the gas becomes relativistic, right, then the velocity cannot go on increasing. The momentum can go on increasing because the mass also keeps increasing. That's a basic fact of special relativity. But the velocity cannot exceed the velocity of light. So you lose one factor of R. Okay. So he said that for a very dense star, when the electrons start moving close to the speed of light, they cannot cross the speed of light, the pressure will rise more slowly as r to the minus 4. And this actually changes physics. That's shown in the next graph. Okay. So, let me see. Yeah, I think you can see me pointing to the graph. So the thought experiment here is to take ordinary matter. So remember, this is a log scale. So 0 means the density of 1 gram per centimeter cubed. So let's say you had hydrogen atoms with a density of 1 gram per centimeter cubed. Of course, now it's not free electrons. And you know that ordinary matter, like what you have in this room, it's very hard to compress it. So the pressure rises very steeply. I've just given a rough formula as r rho to the 5. But at some point, the electrons get squeezed out of the atoms. And interestingly, the physics behind that was illuminated by another physicist of Indian origin, D.S. Kothari. He called it pressure ionization. So this doesn't happen under normal conditions, but under the conditions in the interiors of planets, for example, say the planet Jupiter, the hydrogen is compressed so much that the electrons get freed. You know that the electron orbit is of the size of the Bohr radius. So if you push the protons closer to than the Bohr radius, the electrons don't even know which proton they belong to, right? So they become free. So now it becomes the kind of gas that Fowler talked about. And this rises as r to the minus 5. And then when the electrons become relativistic, and that's a very high density, that's 10 raised to 6 grams per centimeter cubed. Now I told you that the radius of the sun has to shrink by a factor of 100, which means density goes up by a factor of around 10 raised to 6. Okay, so the realization was by Chandrasekhar that this curve will now start rising as r to the minus 4. This is r to the minus 5, and now this is r to the minus 4. Now, what are these curves A, B, C, D? They all rise as r to the minus 4 because they simply describe stars of different masses. So if you have something of the mass of Jupiter, no problem. Have something slightly heavier, but beyond a certain mass, the two curves won't intersect at all. So that is what he realized, and that's called the Chandrasekhar limit. So there's a certain mass, it's about 1.4 times the mass of the sun, and above that mass, there is no equilibrium possible between the inward pressure, if you like, due to gravity, and the outward pressure exerted by the electrons. Now, so what happens? Right? Now, there are plenty of stars which are more massive than 1.4 times the mass of the sun. Okay, of course, so long as the star has nuclear fuel, it can be supported by the normal pressure of hot protons and electrons, or nuclei and electrons. What happens after that? And there was no answer. Okay, Chandrasekhar is not the only person who realized this around 1930. A couple of others. I'm just mentioning their names because now the one interesting name is the third one, Landau, because he's a legendary Russian physicist who himself got the Nobel Prize for his work in condensed matter physics. So it's interesting. Why did these people not share the Nobel Prize? Now, one simple answer is they were all dead by 1983. Okay. But there is another answer. Okay. The first two went into condensed matter physics. Landau actually is a very brilliant physicist. He realized this independently of Chandrasekhar. And he happened to be in Copenhagen under the influence of Niels Bohr, whom you've all heard of, the Bohr model of the atom. Now, everyone tells you of Bohr's successes in physics, but one sort of dark secret is that for 10 years in his life, for good reasons, he thought that energy may not be conserved. That's a different chapter in the history of physics. It has to do with beta decay. And then Landau came under his influence. So he drew the conclusion that if a star is heavier than this limit, he derived the limit, then it will get into a new state of matter and energy will not be conserved and it will happily keep radiating. Okay. So the first part of his paper was perfect. The second part led him astray. Of course, later Bohr, Landau, everyone realized the mistake of that idea. But therefore, it's only Chandrasekhar who followed it up. And it was very difficult to follow it up because he went to Cambridge and the most famous astrophysicist there, the person called Eddington. Eddington himself had written the basic book on stellar structure and contributed to every branch of astrophysics. Okay. And he was a kind of authority. That's why I put THE in capital letters. And he See, of course, on the one hand, Chandrasekhar pursued his ideas, published his papers, and so on. But there was a certain amount of skepticism. And even though the physics behind his calculation was very straightforward, and the physicists in Cambridge had no doubt that the calculation was correct. But as astronomer, Eddington said, and I'll quote some of his famous statements, he said, there should be a law of nature to prevent a star from behaving in this absurd way. Now, what did he mean by this absurd way? The star goes on contracting and contracts till light can no longer escape. Now, actually, we know that there are stars, and we'll see it later in this talk. If it contracts sufficiently, light cannot escape. So Eddington he could have accepted that conclusion, but he did not. He said, this is like a proof by contradiction. You've reached an absurd conclusion, so something is wrong with your physics. Okay? And there's a saying in Hindi that pani mein reh ke magar se vair nahi karna hai. So if you're in water, don't fight with a crocodile. And if you're in Cambridge, you cannot fight with Eddington. On the other hand, we must credit the Cambridge system that they allowed Chandrasekhar to finish his thesis. But then he had to seek his fortune elsewhere. And the place he went to was the University of Chicago. Okay? And he made this decision saying, because of all this controversy, he sat down, he wrote down all his ideas on stellar structure in this book. Okay? And that is a book worth reading, even though on the white dwarf part, it's not changed much. But it gives a nice introduction to thermodynamics and other things, and an introduction to his literary style. Okay. Then he consciously said, I'm going to move to another area. So I've shown you a picture of something called a globular cluster. And I'm sure as amateur astronomers, you will be able to point your telescopes toward a globular cluster. So just to make you jealous, I should tell you that when I came to Bangalore to work in NAL in 1969, there's not much of a city lights, anything there. You could just point the telescope to the south and see a beautiful globular cluster. I doubt that you'll be able to see it from Bangalore, but today, but who knows? Okay. Now this is somewhere between 1 lakh and 1 million stars, and it's beautifully spherically symmetric. Okay. Now it's not practical to trace the orbit of each star. Now, unlike our solar system, there are some differences. Solar system, the gravitational force is dominated by the sun. It's sitting there in the center, and the gravitational forces of the planets are much less because their mass is less. But this is a more democratic system. All the stars have somewhat similar masses. They create a common gravitational field in which they all move. So you can already see it's a more interesting dynamical problem. It's also interesting because it's statistical. Each star does something very different from the others. They orbit in 3 dimensions. Of course, looking at this picture, you cannot say. But if you have 100 globular clusters, all of them look like this. And then if someone says they are all really shaped like a disk, then it are facing you, which is very unlikely, right? So people knew that. And the other reason why they knew it is 3-dimensional is that astronomers can also measure velocities through the Doppler effect. So they could see that these stars had velocities towards you or away from you as well. So this required a different kind of thinking. Now you could say it's a bit like the kinetic theory of gases. The stars are like the molecules. But in the kinetic theory, 2 molecules have to come very close to each other within a few angstroms, and then they collide, and then they go their separate ways. Okay. Now here, the physical collisions between the stars are quite rare. Now you might think they're very crowded in the center, but if you compare the distance between the stars to the diameter of each star, you'll quickly conclude that even over billions of years, the physical collision between 2 stars is very unlikely. However, there is still the equivalent of a collision because of the gravitational force. If 2 stars pass each other at some distance, they will still exchange energy and momentum. So a different kind of kinetic theory had to be developed for this. Chandrasekhar was not the only one, not the first, but probably developed it in a very thorough way. Okay. So he's regarded as one of the founders of this subject called stellar dynamics. Now, this seems to be the only case in his life in which he wrote the book and then realized that he had actually missed something. Okay. So, in the book proper, he put in an appendix on the missing part. The book proper, he worked out how each star can change its momentum under collisions with other stars. It's a statistical process. So, if some of you have heard the word random walk, in velocity space, you have some velocity, which is a vector, then it either gets another kick along the vector or perpendicular to the vector. So the direction changes, the magnitude changes, and you can work out the statistics of this. After all, your statistical institute is not far down the road, right? So this process he called diffusion in velocity space. So any star introduced into this cluster, whatever its initial velocity is, will ultimately achieve this. However, if you only include this process, you're not conserving energy. Every star should be gaining energy. So then he realized that there has to be some other friction. So some star which is moving much faster than the other stars, now it will see all the other stars coming from one direction. And if you work it out properly, you will see that statistically it will tend to lose momentum. So this is more like friction. Okay. So stars with very low velocity get kicked up to high velocity. Stars with a large velocity, much larger than all their other ones in the cluster, get slowed down. And that is the way some kind of equilibrium is achieved. So that is the major contribution. As I said, the anomaly is that his papers on dynamical friction were written about the time the book was in press. So he quickly added them in the appendix. So this was probably his quickest phase. Okay. And then in Chandrasekhar style, he said, I'm going to move on. This doesn't look like astrophysics, right? But the physics behind the clouds is that you have sunlight entering them from one side. The clouds don't actually absorb sunlight that much. The visible light, it's a drop of water is more or less transparent, but the drop can certainly change the direction of. So you have something like the kinetic theory of gases, but now applied to photons. The photons don't collide with each other, but every time they encounter some obstacle, like a drop of water, they change direction. Right? And they undergo this kind of random process. If the cloud is thin enough, some of them come through. So rain clouds are not made of anything else. They are dark simply because whatever light fell on them from the top got reflected back. So if you are above the rain clouds, you would actually see them as white. Okay. Interestingly, the Taj Mahal is made of marble. Marble consists of crystals of calcite. And the different crystals have different refractive indices in different directions. So when light enters, of course, if it enters a single crystal of calcite, some beautiful things happen. But if it enters an assembly of multiple crystals oriented in different directions, the light gets scattered. So the physics of light getting scattered back from marble, or for that matter, even from, if you, okay, this is a very male thing, but if you have to shave, as I had to shave this morning, you have that foam, again consists of small bubbles, light enters it, it looks white. Okay. So all these are governed by a certain mathematical formalism, which is called the formalism of radiative transfer. But of course, this is exactly what happens to light in the planetary atmosphere, like that of the Earth, or in the atmosphere of a star. So all the energy is generated in the center, because that's where the temperature is high and the nuclear reactions can take place. But then it has to come out. And it takes a very long time for light to come out from the center of the sun, radiation, because of this random process of getting absorbed, emitted, scattered, so on. So there's plenty of scope for this subject in astrophysics. Okay. Now, this was a fairly mature subject even when Chandrasekhar entered, but he brought a very nice mathematical touch to it. Okay. And he himself has said that of all the things he did, this gave him the greatest pleasure, because he took some equations which looked almost impossible to solve, and then he found a way of solving them. And the reason why these equations were so complicated is that he also included, which had not been done properly before, the polarization of light. Now, in fact, the polarization of light was discovered in these calcite crystals. That's a separate story. But the scattering of light also depends on polarization. In fact, if you have a simple Polaroid and you look at a blue sky and turn it, you'll realize that light is polarized. And that complicates the mathematics. And he found a very nice algorithm. In fact, computer science people study a similar algorithm called dynamic programming. Okay, but this is not the only thing he did in radiative transfer. One of his colleagues in Chicago realized that in the outer layers of the sun, hydrogen can actually exist as a negative ion. Now, this is very surprising. I just explained to you earlier that at a high temperature, electrons are removed from atoms. Okay, But this brings in another great Indian astrophysicist, Saha, who had given an equation which tells you when ions and neutral atoms will exist in certain proportions, depending on the temperature, but most important, depending on the density also. Okay, so it turns out that hydrogen can have a negative ion, can attach one more electron, but it's very weakly bound, but 1 electron volt. But if there are enough other electrons, you can think of it like a chemist. There's a reaction in which this electron is removed, and there's another reaction, reverse reaction, in which the electron gets reattached. And the rate of each reaction will depend on the abundance of the species. So if you have enough free electrons, you can have H minus. Now H minus had already been studied, but Chandrasekhar realized that you needed to do a proper quantum theory of H minus. So this is his only excursion into quantum mechanics. He gave a very interesting wave function for H minus and devoted enormous numerical work, computer work. So if everyone thinks that he just sat in front of a piece of paper or a blackboard, that's not true. Okay, and computer work was not that easy in those days. In fact, even when I joined NAL, there were computers. There were 2 computers in Bangalore. Can you think of that? One in HAL, one in NAL. But the first calculation that I was asked to do was done on a hand calculator. So you had to do something like this, to add, subtract, and so on. Okay. So fortunately, Chandrasekhar had a very devoted assistant who did many of these calculations for him. But early on, he had to do them for himself. Okay. So in any case, this was the radiative transfer phase of his career. And I think that book is 1950, right? Then he moves again. Okay. So talking of fluids which are electrically conducting, so the first one which comes to mind is element like mercury. But also, even if you take iron or something and you melt it, it's still a metal. So that's a conducting fluid. And the important thing is that if something can support an electrical current, it'll generate magnetic fields. Now, this is an idea which has already been explored in the context of the Earth's magnetic field. See, of course, long ago, people might have thought that at the center of the Earth, there is a big bar magnet. But we know that's not true because the center of the Earth has a much higher temperature than the outside. In fact, the temperature, the center of the Earth is roughly the temperature of the surface of the sun, thousands of degrees. And if you take iron and take it to thousands of degrees, it loses its magnetism. It melts. However, it is a conducting fluid. And something remarkable happens. Because heat is flowing through this liquid interior of the Earth, some kind of convection is taking place. So now you have a conducting medium which is moving, and it can act as an electrical generator. Okay. So this is quite a remarkable thing. The sun has a magnetic field, and the temperature of the center of the sun is such that no solid or metal can exist. It still has a strong magnetic field, which is seen in sunspots and so on. And there again, you have a situation where some kind of dynamo seems to be operating. Now, Chandrasekhar did not work on the dynamo itself. In fact, one of his colleagues in Chicago called Parker, who only passed away very recently, was the sort of king of dynamo theory. But in any case, Chandrasekhar realized that fluid mechanics had not been sufficiently investigated in the presence of a magnetic field. And he devoted, quite a few years to the study of this. It could be compared to laboratory experiments. And in the laboratory itself, you encounter a related situation in what is called a plasma. Now, plasma might be very important for our future because one of the sources of energy which is being talked about is fusion energy. India has already invested a major amount in an international project called ITER, International Thermonuclear Experimental Reactor. Okay. And the idea there is that the same reactions that take place in the center of the sun, you will do on Earth and you will get energy, supposed to be cleaner and so on. So at any time from 1950s, people have said that nuclear fusion will be achieved in 10 or 20 years. Okay, that's still true. So it's a bit like a flight where they keep telling you that it will leave in 1 hour, but it never leaves. Okay. I mean, I'm being a little cynical here because it's a very difficult problem. But people are making progress on this. So fusion plasmas also are an application of this kind of theory. In fact, Chandrasekhar has a book which I did not mention because he didn't write it. It was written by his student. like his lecture notes on plasma physics. Okay, and that student again is an Indian, Professor S.K. Trehan. Okay, and so he devoted and he developed some very interesting ideas. Okay, uh, instabilities. Some of them seemed very academic. You know, you have something which is rotating, which has a magnetic field, and then you disturb it, and is it stable or not? But Chandrasekhar seems to have had a kind of, I don't know, green thumb or Midas touch. Some things which he worked out purely for the sake of the theory turned out to have application later. And that is certainly true of the work he did in this field. It's also his thickest book. I had occasion to refer to it when I was doing some work on white dwarfs, and I can assure you it's pretty thick. And this is the important point, that the results seemed very academic at that time. Okay. So now we are nearing 1960. Okay. Now he takes a giant step backwards. Okay. Now this is a very exciting time in astrophysics. All kinds of objects are being discovered. General relativity, Einstein's theory of gravitation is being used. And privately, he's studying Einstein's theory of gravitation. Right? It's a beautiful mathematical theory. So who would not be attracted by it, right? But he is also very principled. He said that, look, I cannot, since I'm learning this subject myself, I will not work with students on this subject. I'll work on a subject in which I have complete mastery and control. So the subject he chose is called Ellipsoidal Figures of Equilibrium, the title of the book. Okay. And it starts with Newton. Many of you may know that the Earth is not a perfect sphere, slightly flattened because of its rotation. Okay. Now, Newton himself worked out how much it would be flattened. Okay. But he gave a solution only for slow rotation, which is enough for the Earth. It's about 1/3 of 1%, something like that. Difference between the radius in the polar direction and radius in the equatorial direction. Okay. But one of his successors, a mathematician named Maclaurin, I'm sure all of you have seen the Maclaurin series for expanding a function in powers of x. Okay. He worked it out for any speed of rotation. And the sphere becomes what is called a spheroid. So you take the equation of sphere x squared by a squared plus y squared by a squared plus z squared by a squared equals 1 and make the three denominators unequal. If all three are unequal, it's called an ellipsoid. So that is the Maclaurin spheroid. Okay. Then another mathematician came along called Jacobi, and he said, this Maclaurin spheroid, let's imagine we go on giving it more and more angular momentum. At some point, it has a rotation axis, and the remaining two axes are equal, but it prefers to make the two axes unequal, make one axis longer. So now all three axes are different. So that's called the Jacobi ellipsoid. And this is a very idealized problem where you have a fluid under gravity. Okay, and it doesn't resemble any astronomical object at that time. Okay, which is why I said Chandrasekhar took a giant step backwards. Mainly attracted mathematicians. I've mentioned some of them, Riemann, Dedekind, and so on. But Chandrasekhar obviously had read this theory. He found a lot of questions unanswered. Are these stable? So on and so forth. So he decided to look into it himself. And he completely almost cleaned up the subject. He introduced a new tool, which you could do. And he had a student who worked on it, who continued to work on it. And now we have come to 1969, 1970. At this point, he decided he would now start plunging into the general theory of relativity. Okay. And some of the motivation for that also came from the fate of stars. I sort of left things hanging. What happens to a star when its mass is above 1.4 solar masses? Now, of course, the initial mass of the star might be 3 or 4. If it is able to get rid of some mass, and all stars do get rid of mass, right? They have some kind of wind. So then if it comes less than 1.4, it can settle down. But you have stars whose masses go all the way up to 50, 60, 100, right? We know that today. So what about those stars? Now, one of the interesting answers which came about, electrons become relativistic. The next thing which can happen is that the electrons can actually combine with the protons and become neutrons. Now, this is the reverse of what happens if you have a free neutron. If you have a free neutron, it decays in about 800 seconds to give you a proton, an electron, and a neutrino. The neutrino was not detected for a long time, which is why Niels Bohr thought that energy is not conserved. But once the neutrino was introduced, it's clear energy is conserved. This is called beta decay. And what happens in the interior of a very dense object, much denser than what we talked about, not million now, grams per centimeter, much more, is that you get reverse beta decay. The electrons combine with the protons. So you now can get a neutron star. And there's this very popular movie called Oppenheimer. So one of the first people who worked it out was Oppenheimer with his student. Okay. In fact, he wrote 2 papers, which are both very fundamental, before he became the head of the atomic bomb project. One was on the neutron star. Okay. But of course, the paper was pessimistic in the sense the forces between neutrons were not that well understood. So he came up with an answer that the limit, equivalent of Chandrasekhar limit for a neutron star, is more like 0.8 solar masses. Okay. Then the other paper, which he wrote with another student, said that if all this doesn't work, the star will keep contracting until light cannot escape. So the possibility which Eddington had ruled out as completely stupid was actually shown to be a consequence of general relativity, Einstein theory of gravitation, by Oppenheimer and his student, Snyder, I think in this case. Okay. So, fine. There was this concept of a neutron star, right? But when was it discovered? 1967, in a completely different way by someone who was not looking for it. And this is again a beautiful story of radio astronomy. I have to actually look at my time. Okay. I do have some time, right? I think I started around 11:40. Yeah, okay. So then I'll tell you the story. That in the same Cambridge, a radio astronomer called Anthony Hewish wanted to study the equivalent of twinkling of stars. So radio waves come through the Earth's ionosphere and also through the plasma surrounding the sun, and they get bent, and the intensity can change. So he built a radio telescope just for that, and he put his research student called Jocelyn Bell on that. So she kept, and there were no computers in those days, so the intensity coming out of the radio telescope would be recorded on miles and miles of paper. And then she found one day that there is something which is very periodic, very regular. And initially no one believed it because in radio astronomy you can also get signals from anything, from a motorcycle, from a microwave oven, anything, right? But she proved that these signals are coming from space by a very simple argument, which all of you should appreciate. The signals came 4 minutes earlier every day. So if you look at the rising and setting of a star, for example, it's 4 minutes earlier every day, right? Because the Earth actually turns with respect to the stars in 23 hours and 56 minutes. With respect to the sun, it turns in 24 hours because the Earth has moved a little bit in that one day. So in any case, once she proved it, regular pulses in radio waves, immediately people started working on it, and they concluded that it had to come. I'm skipping a lot of physics. You should get a separate talk on neutron stars from the right person. It's the next stage after the white dwarf. As you go on compressing, you end up with a further factor of 1,000 now. So going from 10,000 kilometers to 10 kilometers. So you have to imagine something with the mass of the sun concentrated in this, not the size of the Earth, that's a white dwarf, but concentrated in the size of a small city, right? It's unbelievable. It has the density of an atomic nucleus. It's a giant atomic nucleus. Now, such an object also requires general relativity because it's so compact. See, the escape velocity from the surface of a neutron star could be 1/3 the speed of light. So at that point, you can't apply Newtonian physics. You have to apply, right, relativity, right? So all these exciting things were happening, right? Now, so Chandrasekhar began working in relativistic astrophysics, okay? He never wrote this part up in a book. Okay? He worked on rapidly rotating neutron stars. And then a binary system, 2 stars going around each other, general relativity produces a new prediction. That if 2 charges go around each other in electromagnetism, they emit electromagnetic waves. And long ago, Einstein had said that if two masses go around each other, they will lose energy in the form of gravitational waves. It's so weak that people thought it could never be detected. It's also technically a big challenge to work out this with general relativity. And Chandrasekhar took up that challenge. And again, he improved on whatever had been done. Okay. But this found an immediate application because in 1974, again, radio astronomers discovered a pulsar which was going around another neutron star, and the orbit kept shrinking by a very small amount, but detectable. And this was the first evidence for gravitational waves. So clearly, general relativity had become very important in astrophysics to understand the structure of individual neutron stars or binaries. So Hulse and Taylor are the people who got the Nobel Prize for gravitational waves. Now, these are very difficult calculations. And we are now talking of a person who is, well above 60. And he had very young students. So many people would just tell the student to go and do the calculation. But Chandrasekhar checked everything that they did himself. Okay. And that's amazing. Right? And nowadays you can do algebra by computer. So I don't know whether I'm giving away a secret, but I think all of you are very IT savvy. If you want to differentiate or integrate something, you don't have to remember it. You can go to some software called Mathematica or something and type it in. And that's even before AI. Of course, with AI, it becomes even easier. So people did some of these calculations by computer algebra. It's not trivial because you have to feed your problem correctly. And then when they checked Chandrasekhar's calculations with hundreds of terms, they found all of them were correct. Okay. Now, neutron star itself can go up to 2 or 3 solar masses. What happens to a star where the remaining part, after it has exhausted its energy, after it has thrown away some mass, what happens to it? And the answer is what Eddington had said long ago but not believed, what Oppenheimer and Snyder had said happens. It just contracts. It doesn't reach any equilibrium. In fact, the matter of the star passes through a surface, which is called the horizon. And from that surface, light cannot escape to infinity. From inside that surface, light cannot escape to infinity. And this is what you call a black hole. Again, right? Black holes is a subject on which you should have the right person talk to you. Now, the purpose in this story is to tell you that by this time, middle of 1970s, Chandrasekhar decided that he was going to work on black holes. So not just on astrophysical relativity, but black holes. Now, black hole is interesting because this matter has actually passed through the surface and is not communicating with the outside. So as far as general relativity is concerned, you're dealing with the equations for vacuum, but with a particular kind of boundary condition at this horizon. What I have described for you is a simple black hole. There is also a solution corresponding to a rotating black hole. And Chandrasekhar was fascinated by this. If you read the introduction to his book, which you can definitely read, he says, this is the most beautiful object because astronomical object, because you don't require to know anything, any physics of matter. You only need the physics of gravity and vacuum. Okay. But there were these two solutions, but people didn't know were they stable? If you disturb it, what would happen, and so on and so forth. A very difficult mathematical theory. Okay. This is also the period where his health started to fail. And some of his students have recorded that he had a heart condition and almost every possible complication that you can get, he went through. But he postponed the surgery because he wanted to finish his book. Okay. So he did finish the book. Okay. Called The Mathematical Theory of Black Holes. And in fact, I should also mention that Chandrasekhar, I told you he was a nephew of C.V. Raman. And there are other nephews through his sisters and so on who stayed back in India. One of them was my thesis supervisor. So Chandrasekhar himself would drop in Bangalore and to the Raman Institute. So we had a chance to hear talks by him in 1970s. And it was clear that he was enthusiastic about black holes in the way that a fresh student is. Okay. There's so much excitement in his voice when he talked about it. I'm talking of 1975. In another 10 years, he'd written the book. And he still could not put all his calculations in the book. He put them in the library. And again, in this period, he was working with very young students. So that is the sixth phase in his life, which I have come to. Okay. And you can now see the pattern in his life. Chooses an area which may not be the most fashionable area. Okay. It appeals to him because of maybe the mathematics. So in that way, it's a little different. There are astrophysicists, very good ones, who will immediately, when pulsars are discovered, they will work on pulsars. Then when the next gamma ray burst is discovered, they'll work on that. That's one style of working. But his style is to find a problem which would sustain him. And, where you could develop some beautiful theories. And of course, remember, he was not alone. There were other people also competing with him, right? And the important thing is to move on. And there, I think he's pretty unique. Okay. Now I want to talk about one more book. And that, again, is not included in my list of 6. And not because I wanted to stop at 6, but because it's a very different kind of book. Okay. It's not original research by him. It is his own tribute. The master. Now, whom would Chandrasekhar, a man of his stature, think of as a master, right? And the answer is Newton. Okay. So then he took one more step backward and took Newton's famous book, Principia, which is reputed to be a very difficult book. Not because it's in Latin. That's the easy part, because people have translated it. But even after it's translated, Newton wrote in a very unique style, geometry and so on. Many people have commented on Principia. So Chandrasekhar is not at all the first. What he decided is, I will ignore all the commentary. Even our own famous religious texts and so on have lots of commentary written on them. He said, I'm going to ignore that. I'm going to read it as a physics book. Okay. And I look at each result. I'll work it out the way a modern person would work it out. And then I'll compare it with Newton's derivation. Okay. Now, we are talking of a person who is now, right, in the 1990s. Yeah, you're talking of that. So he's now past 80 years old, and he's sitting down, going through Newton, re-deriving everything for himself. Okay. But this is now a labor of love. Obviously, he's not going to publish these derivations except as a book. And this notion of a common reader is kind of interesting. Okay. I don't think this quote is easily readable, so I'll read it out. Interestingly, Chandrasekhar also had a deep knowledge of literature, music, and so on. So in this case, he's quoting Samuel Johnson, who was one of the giants of English literature, of the English language, I should say. Gave one of the first dictionaries and so on. So on the one hand, these people are great literary critics, right? If you study literature, you have to study the critics. You can't just study the original book. But Johnson says, I rejoice to concur with the common reader. And he goes on to say that ultimately, that's the person who really counts to say whether a work is really great or not. Okay. So Chandrasekhar said, I'm a common reader. So the common reader is not you and me, it's Chandrasekhar. And I'm going to read Principia. Okay. This book was published in 1995, and that's actually the year he passed away. So you can see that he was working absolutely till the end of his life. In fact, it's probably true that if he had had a little more time, this book has unusual large number of, errors and so on, typos and so on, as compared to his other books. He was extremely careful. There are many things about him that I have not told you. While doing all this, he was a very long period, I think 15 years or more. He was the editor of the major journal of astrophysics called Astrophysical Journal. Every paper which came there, he would look at it carefully, decide who could referee it, or he would referee it himself. He kept up the quality of the journal. So I hope I've given you a feel for the different phases of his career. And certainly I hope the details of his Nobel Prize winning work based on basic physics have come across. And the other things, it's a bit like these tourist buses, they take you to Mysore and quickly show you various things, hanging gardens, Vrindavan gardens, so on, and then bring you back. And then, of course, you have to go later if you find something interesting. And so the same applies to this. If any of you are more interested in the subject, I can certainly point you to some place where you can learn more. But I think this was a good opportunity to convey to a bunch of young people interested in astrophysics about this very remarkable astrophysicist. Thank you. Here the surface, the matter is not in that form. The matter is in the form of normal nuclei and electrons. The pressure there is not that high. Okay. Go to the interior. The electrons, again, because of exclusion principle, enthalpy principle, and exclusion principle, the electrons form a Fermi field. Yeah. So if the neutron has to decay, that electron cannot come out with zero energy. It has to come out with energy on top of the Fermi field. So as you go to higher and higher density, that Fermi level rises, and then the neutron becomes stable.
Also, I've heard about, like alternate matter stars, like something like strange stars and quark stars. So that's where. Okay. I see. Okay.
So whether there is one more state much denser than the neutron star, even if it is, what is now happening is, what I didn't mention, the radius of the neutron star is already approaching the kind of
Right, yeah.
beyond which so what in strange stars doesn't possible. I do see papers suggesting ways of distinguishing them from ordinary stars, but they are not going to go up to relatively high masses and small radius.
I see. Thanks.
So theoretically and experimentally, we know the neutron stars have like trillions of Tesla magnetic field, basically. Magnetic field strength. It's in trillions of Tesla. But the basic idea of quantum electrodynamics and basic idea of magnetic field is because of electrons, the flow of electrons or current. But the problem is in neutron stars, especially as this last, like the number of electrons is very less. And because of density, most of the interaction is with the Higgs field. There's no interaction much with the electric field. Then where is the magnetic field coming from?
Okay, fair enough. Yeah, if you only had neutrons, I agree. How are they going to carry a current? However, what I described to you is a chemical equilibrium between neutrons and a small number of protons and a small number of electrons. If you didn't have those protons and electrons, then what we said would happen? The neutron would be. So most protons and electrons, although the number may be small compared to the number of neutrons, it's still a very large number. So they can carry current. No problem.
So, but because most of the interaction is with the Higgs field because of the mass and with strong and weak nuclear forces, won't the electric field get tampered? Then how is it producing very high currents? In black holes case, even though there's electrons, you don't observe that high magnetic field. It's only pulsars. You don't get the equal magnetic field of a neutron star. Why is it so?
After that, they behave just the way that particles behave. They didn't change their behavior. So I would still say that even if the electrons and protons get their mass from the Higgs field, that doesn't prevent them from carrying current. Now, the value of the magnetic field, which is taken from Gauss, so remove 4 power, Tesla or something, very huge. And that has been explained. If you take one of the principles of plasma physics is that if you have a conducting fluid has a magnetic field and you compress it, the magnetic field lines also get compressed. So if you just scale up the magnetic field of the sun, you get pretty much the right value for white dwarfs and neutrons. And it's very rough. Now, the other question is, do these currents decay? So one of the interesting ideas is that the interior of the neutron star could be superconducting. Then the current is not. But even if it decays, then the question is, what is the time of it? Anyway, I think you're familiar with LR spectrum. You know that inductor is something that shows magnetic resistance. And if there's resistance, it will decay on some time scale, but maybe the time scale is very long.
So, but logically, it doesn't make sense. If you look at the singularity of a black hole, where temperature is near zero, yeah, it's related, sir. If you're looking at the black hole,
Telling him, exactly. I'm telling him. Yeah.
Not a particle physicist. What do my depth here?
Yeah, sure.
No, but I don't want to make a general point. It's not physics on different scales. Okay? Now, people are making new discoveries at very small scale. But that doesn't mean that the basic physics that we learned on larger scales is completely different. Even Einstein's theory of gravity is completely different from Newton's theory. But it has to give all the same predictions about planetary orbits with small corrections. So, you have Higgs field, your quarks, so on. But whatever you learned about a nucleus and a proton, electron going around is valid.
sir, what is the significance of dark energy and dark matter in the modern day astrophysics, and how is it related to black holes, according to you, sir?
Dark matter has been around from 1980s. Dark energy from 2000. And dark matter is on the scale of galaxies and clusters discovered, and dark energy on the entire scale of cosmos. They're not directly connected to black holes.
What are the unanswered questions yet in black holes, related to black holes?
Black holes are actually objects which emit a huge amount of energy. Not from the surface itself, but from matter which is close to the surface, it has become extremely hot and we have a magnetic field around now. It's called accretion of the black hole. So, accretion of the black hole is the subject which is still under active investigation. One big Philip discovery got in 2019 was when people were actually image. You might have seen the ring shaped image. Black hole image. So, at last, this inner region was too small to ever be seen. People only had to figure it out. So today, people are actually modeling it and comparing it to observations. So about the black hole itself, the theoretical question which people are still trying to answer is the stability of the black hole. I mean, today these questions are also attacked by means of something. There is something called numerical relativity. In fact, one of my studies was very smart and expert on that. As far as the numerical relativity people are concerned, black holes are there, they're quite stable. But mathematicians would still like to prove. And that is the problem which Chandrasekhar tried very hard. Maybe I should mention, I should say this. There are two kinds of black holes. Short shield is the one which is not rotating. The stability of that was investigated by a person called Chandrasekhar from Bangalore, actually from Chennapatna. He did this work in Maryland. He came back, worked in Bangalore, set up the planetarium. Very well known. But you should really get someone to talk to you about that.
Thank you, sir.
As a radio
trying to get proper signals from outer space. And given that Elon Musk is shooting satellites at the rate of 100 every minute, what do you think would be the ground-based observations that we can do using radio astronomy? Like for amateur radio astronomy or small clubs like us that we would like to pursue, what do you think would be the next course of action?
I think the small clubs are actually fine because they will look at really bright sources. The problem is that if you're looking at the faintest possible sources like the GMRT, then even nearby airports and other things can cause lots of problems. And these satellites, in fact, I left there in 2010. At that time, in the data, I would rarely see the satellites. I mean, when I say I see, but when I visited there recently, they now routinely have a software to remove these satellites. Once this huge number comes up, it also depends on the frequency band. But the problem is, Elon Musk may be legal because he may be radiating in a band which is allowed. But unless you build perfect electronics, even if millions of that power goes outside that band, then radio astronomy is fixed.
Because they recently I read that there is something called as UEMR, unrequired radio signals that are coming from satellites because of the sheer amount of satellites that we have launched and some dead satellites also which are just orbiting the space. So in fact, a couple of space agencies are mooted to push radio astronomy outside the sphere of satellite influence and set up.
Modest budget of 40 crores. You wanted to put radios over the moon, it might be some 4 lakh crores or something. Yeah. So radio astronomy certainly is facing a problem. One curious thing is that places like Antarctica, many of these satellites don't pass over the poles. This is a worry. And the bigger worry for the world community is, over some 20 years, people have invested in a giant project, much bigger than GMR. Group also part of it, called SKA, Square Kilometer Array. Now that has something in South Africa and something in Australia. Now, as far as human interference is concerned, those things are fine. In fact, I remember attending meetings where the South African person show how good their site was. They'd show a picture and you'd only see lines. You wouldn't see any human being. But
So that brings us to the end of this session. Thank you so much, sir, for coming, sir. And this event would not be possible without our principal support, without telecom department support, and IQACRDC, and special thanks to Department of Physics and Devdata sir, ICTS outreach team. We kept on delaying the dates, but they were still patient. They held on to us, and this event was possible. And thank you so much for showing up. We are glad you were here, and we hope you enjoyed this session. Thank you so much. Streaming on